guys, this is Academic Chem, Chapter 3, Section 1, Part 2. So in this section, we're going to talk about taking measurement and what it means to be accurate versus precise in chemistry. So first, I want you to imagine that you are told to throw a ball, football, baseball, whatever, and hit this whole target. Now remember that this is generally projected on a giant screen behind me in class. So this is now a giant box that you have to hit. Do you think you could throw the ball and make it on this box? Okay. What if this was the size of the box? Would you be able to get it in the box then? Think about that, and I want you to let that marinate, and we're going to come back to that later. All right, what is accuracy? So the great thing about this in science is accuracy is just like regular English. Accuracy is how correct a measurement is, or multiple measurements. So did you get right what you're supposed to get? So for example, the boiling point of water is known to be 100 degrees Celsius. That is just a known fact. So Bob measures 3 different waters that are boiling, and he gets 99.9 degrees Celsius, 100.2 degrees Celsius, and 99.7 degrees Celsius. So is he accurate? Well, is he correct? Is he like right there on the right answer? Well, if you notice all of these, if you chop off that last sig fig, pretty much rounds to 100 degrees Celsius. So yes, since they all round to 100 degrees Celsius, he is basically correct and therefore accurate. Now some scientists will say accuracy is like within 3% or 7%. I like to think of it as are you right there? Like just you've got to be really, really, really close to be accurate. All right, so versus Chad here. So Chad got 88.6 degrees Celsius when he did his tests for boiling water, 88.3 degrees Celsius, and 87.8 degrees Celsius. Is he accurate? Well, are these measurements all pretty much 100? No, they are not. So they all round to this 88 degrees Celsius, which is not 100, so he is not correct and therefore not accurate. All right, precision, however, precision is how repeatable a measurement is. And there's 2 types of ways to be precise. So this can relate to a series of measurements, all rounding to the same measurement. So are you constantly getting the same thing? Or it can relate to the ability for another scientist to exactly replicate a measurement based on having the most sig figs. We're going to talk about the first definition first, so all numbers in all your calculations all rounding to the same measurement. All right. So precision, again, how repeatable a measurement is. So Bob got 99.9 degrees Celsius, 100.2 degrees Celsius, and 99.7 degrees Celsius. Is he precise? As in, did he repeat just about the same number each time? So yes, they all round to 100 degrees, so all of them are pretty much the same thing, so he is precise. How about Chad? Chad was not accurate because he got all his numbers were around 88, which isn't 100 degrees Celsius, but was he precise? Was he getting the same thing every time? And yes, he was precise. So although Chad was not accurate because he wasn't getting close to the right value, he was precise because he kept getting the same thing. That's the thing. If you are not accurate but precise, you can kind of analyze the situation and say, it's probably something wrong with what I'm measuring. Like Chad might not have been using water. He might have accidentally gotten some alcohol or something and then not noticed. Maybe something's wrong with his thermometer because he keeps getting the same wrong answer. So something's wrong here, and that can help you kind of evaluate the situation. All right, so here's some graphics. Let's compare and assess, is this person that's throwing darts accurate or precise? So over here, we've got someone that hit all the darts right here, but they missed the bullseye. So this is where you want to hit when you play darts. So are they accurate? No, they didn't hit the right spot. But are they precise? Yes, because they kept repeating. So this is how it would look if you're precise, but not accurate. Over here, we've got 4 darts in 4 different places. So you're not accurate because it's not hitting the bullseye, and you're not precise because you're not repeating the same thing each time. So this is neither precise nor accurate. Down here, I've got all 4 darts hitting the bullseye. By the way, I do not do this when I play darts. I don't even hit the target at all, so don't ever pick me for a dart team. But if you find someone that can do this with the darts, that's who you want on your team because they are both precise and accurate. They're getting the right place and they're repeatedly getting the right place. So it's the same every time, it's precise, and it's correct every time, so it's accurate. Let's go back to this. If you have a giant target to throw a ball into a box, you might get it in the box, and the next person might also hit the ball in the box. But will it look exactly the same? Imagine one person throws the ball and it gets in the box over here. Okay, sounds good. Another person throws the ball and it hits over here. Both got in the box, but it didn't happen exactly the same way. The bigger area of estimation in your measurements of chem, the more difference there can actually be that you won't really notice. Versus, let's say you have balls and you throw it in this box. If someone hits a ball here versus over here, it's a lot more similar of a throw versus both hitting in this box. So that relates to chemistry if you look at this. Which measurement is the most precise? Meaning, if you were to repeat this measurement, which would be actually most similar? So if you were to repeat 54.2 meters or 54.2, yeah, or 54 meters or 54.81 meters. Remember that the last digit is estimated. So that means this 2 is maybe, this 4 is maybe, and the 1 here is maybe. Which of these has the smallest amount of unsure of? That's going to be your most precise measurement, because if you repeat that measurement, then you have the smallest amount of estimation. So which of these measurements is the most precise means what do you know the most about, or what's the least amount of unknown. So what you want to do is you want to make sure they're all with the same unit. They're all meters. And then you want to see what's the last digit to the right. What position is it? This is the tenth. This is the units, and this is the hundredths. Which of those is the smallest? The hundredths. So 54.81 meters is going to be the most precise out of those measurements. Think about this first one. If someone else took a measurement and they said 54.1 meters, that would pretty much be the same measurement. If someone else took a measurement here and they said 55 meters, that would pretty much be the same measurement. You have a much bigger degree of change here. Smaller degree here, and even smaller here, because 54.82 maybe could be a measurement someone takes with the same thing, and that only changes by 0.01. So that's the smallest degree of estimation, or the most precise out of all of these. How about this series of measurements? Which is the most precise? As in, if you were to repeat this measurement, which would definitely be the most similar if you got the same results? So would it be 8.431 liters, 47.2 milliliters, or 4.6 centiliters? So which is the most repeatable? As in, if you got the same thing, is it definitely the same? Well, the first thing is, do they have the same unit? So liters, milliliters, and centiliters are all different amounts, so you have to convert them. So you have to convert to the same units. So I'm going to get rid of prefixes. So my first one, 8.431 liters, doesn't have a prefix, so that stays the same. But 47.2 milliliters, milli is your prefix, so you replace that with 10 to the negative 3. So now I have 47.2 times 10 to the negative 3 liters. So the milli got replaced with 10 to the negative 3. 4.6 centiliters, you have to replace centi, which is 10 to the negative 2. All right, so now wherever you have a 10 to the power, you have to move the decimal to match that power. So my first one, 8.431 liters, has no 10 to the power, so that stays the same. 10 to the negative third, negative means your decimal moves to the left 3 times. So that gives me 0.0472 liters. Versus 4.6 times 10 to the negative second. The negative means my decimal moves to the left. If it had been positive, it would move to the right, but it's negative. It goes 1-2 spots. So 0.046 liters. Now we can really assess which is the most precise, as in which measurement is the most exact, because it has the smallest amount of estimation. So this estimation is in the one, where the 1 is, which is the tenths, hundredths, thousandths position. Versus our thousandths position here is known. We know for a fact that this is definitely a 7 it's even smaller that's estimated. Over here, we've got thousandth as well. So our middle value, back to our original, that 47.2 milliliters, that's the most precise, as in if we were to repeat it, we would know for a fact it was the most similar or repeated from our original measurement. I hope that helps, and good luck with this section. Okay, bye!